Hello everyone. Welcome to the second part of the introduction to Verilog HDL lesson series. And now that you have got to know what Verilog HDL is and the importance of it, we can look into more technical details about Verilog. In this part, we'll look into the basic concepts of Verilog. So you will need to know these concepts to implement or design something using Verilog. And as I told you in the first part as well, you can refer to the Verilog HDL reference book to get more information or knowledge about what we are covering in these lessons. And what we'll be discussing in this part are relevant to the content in the chapter 3 of reference book. So if you need to get more information regarding what we are covering in this part, you can refer to the chapter 3 of Verilog HDL reference book. Okay, now we look at the outline of what we will be covering today in this part. First, we'll be looking at the lexical conventions of Verilog, and then we look at different data types available in Verilog, and then finally we will look at system tasks and compiler directives which can be used in Verilog. So this is the outline of what we will be covering today, and we'll first go to lexical conventions part. So lexical conventions are the basic syntax that you can use in Verilog. Now you all know that in C you have syntax that you can use. If you don't follow them, you will not be able to write a valid program in C. The similar concepts apply here as well. And the basic lexical conventions used by Verilog HDL are also similar to those in C. So since you all are familiar with C, it will be a bit easy to go ahead with Verilog. Now Verilog contains a stream of tokens. So tokens can be comments, delimiters, numbers, strings, identifiers, and keywords. So we'll look at each of them separately little later. And Verilog is also case sensitive, just like it is with C. The Verilog is also case sensitive. So when you are defining variables, rather you will use things called wires and registers in Verilog. So when you are defining such wires and registers, you need to be aware that they are case sensitive. And all keywords used in Verilog are in lowercase. That is also similar to what you see in C. So first we'll briefly look at white spaces, how white spaces work in Verilog. Blank spaces, tabs, and new lines comprise the white space. So they are all considered as just white space. White space is ignored by Verilog except when it separates tokens. You have seen this in C as well. And white spaces in strings are not ignored. So that also you have seen in C. So if we talk about comments that can be used in Verilog, the comments can be inserted in the code for readability and the documentation, as you already know. And a one line comment starts with 2 slashes. So this is also similar to the way you put comments in C. And a multiple line comment starts with a slash and a star and ends with a star and a slash. And multiple line comments cannot be nested. That is, you cannot insert a multiple line comment inside another multiple line comment. However, one line comments can be embedded in multiple line comments. And here there are a couple of examples given for comments that can be used in Verilog. So the first one is about a single line comment, and the next example is about a multiple line comment, and there's an example for illegal comment, and the fourth one is about embedding a single line comment inside a multiple line comment which is valid. So that's about comments, and now we can look into the operators that can be used in Verilog. Now operators in Verilog can be classified into three types: unary, binary, and ternary. So this is also very similar to what you see in C. Unary operators, they precede the operand. You place the unary operator before the operand. And binary operators, they appear between two operands. And ternary operators are also available in Verilog. They have two separate operators that separate three operands. So most commonly you will be using the unary and binary operators. You are allowed to use ternary operators as well. Now you will understand what they mean better with these examples given in the slide. The first example is about a unary operator. If you want to assign the negative of b into a, you can use this unary operator that negates a variable a equals not b. So this is a unary operator. And the second example is about a binary operator. That's about taking the AND of two variables or conditions. So a is equal to b and then c. So you place the binary operator in between two operands. And the third example is about a ternary operator. There you have this syntax: a is equal to b question mark c colon d. So there what it says is if b is valid, assign c to a, otherwise assign d to a. So this is kind of like a short form of if conditions. So I think this syntax also you have seen in C. So here in Verilog also this syntax works in the same way. So this is about the classification of operators, and now this table lists all the operators that are available in Verilog. So the operators can be classified into different groups as it is given in the table as well. Operators can be arithmetic operators, they can be relational operators, logical equality operators, etc. So arithmetic operators, the examples for arithmetic operators are plus, minus, multiply sign, divide, percentage sign. So these things you already have seen in C. And relational operators are smaller than sign, smaller than or equal to sign, greater than sign, greater than or equal to sign. So these signs. And logical equality operators, equal, that is used to check whether two values are equal, and things like that are there. You can refer to this table if you need. So most of the stuff here are very similar to what you see in C as well. And this is something important regarding lexical conventions in Verilog. This is about the number specification. So this section or this number specification might be something new to you, because this something like this is not seen in C. You don't have similar syntax in C to specify numbers. Now we'll see how this works. This actually is about how you can specify numbers or how you can define numbers in Verilog. So when you are using numbers in C, you are just inserting the numbers 1, 2, 3, 4, 5, 175, things like that. You just enter the number, use the number. But here, when you are specifying a number inside the code, you have other options to describe the number precisely. That is, when you get an example, you will understand this better. Anyway, we'll look at the general syntax first and then go for an example. If you are going to specify a sized number in Verilog, this is the syntax that you have to use. You first have to specify the size of the number and then apostrophe sign and then base format, and finally the actual number that you need to insert or specify. Now this size is the number of bits in a number in decimal. So it is like, now say for example you take the number 10 and you can represent this number 10 in say like 4 bits, and also you can represent the same number in 8 bits, and also you can represent the same number in 100 bits. So that is possible. So this size means the number of bits to be used to represent this number, and the base format is used to specify the base to be used when representing the number. That is, you can specify whether you are going to write the number in decimal, hexadecimal, binary, or octal. And the number part is the actual number that you want to insert. So this can be written with digits from 0 to 9, and even you can use these A, B, C, D, E, F letters if you are representing the number in hexadecimal format. Now all these things will be more clear when we look at a real example. Now the first example, if you look at it, that is a 4-bit binary number. This is because the first digit in that number specification is 4. So that 4 is used to specify that it's a 4-bit number. And then apostrophe B is used to specify the base format we are using to represent the number. So here it's binary. So we need to enter the number in binary. So the real number here is 1111. So you can calculate the decimal equivalent to this one. But anyway, we wanted to represent it as a 4-bit binary number, and we have represented it that way. And the second example is a 12-bit hexadecimal number. So with 12 you specify the size of the number, and with the apostrophe H you specify the base format to be used. So the base format to be used here is hexadecimal, so you use apostrophe H. And then ABC is the real number that we need to represent. So ABC, they are all hexadecimal digits. And the third example, there we have specified a 16-bit decimal number. So the first part of that number is the size of the number, 16 bits. So we have included 16 there, and apostrophe D is there to specify the base format to be used. It's decimal, and 255 is there as the number, the real number we want to enter. So that's it. I hope it was clear. We were talking about sized numbers. Now here we are going to talk about unsized numbers. The only difference here is that you don't specify the size. So the size part is missing here, and the base format and the number work in the similar way it worked with sized numbers. So the numbers written without size have default number of bits, that is simulator and machine specific. So the size we are not specifying here. So the size is taken to be a default number that is decided based on the simulator and the machine on which the design is simulated. So this size must be at least 32. Usually when we want to represent an exact number with exact number of bits, we go with size numbers, not with unsized numbers, because in unsized numbers we don't know the size, that is like the number of bits that is used to represent the number is not known to us when we are using unsized numbers. Numbers written without base format are decimal numbers by default. If you don't specify the base format, then the default base format that is used by the by Verilog is the decimal format. So the first example given here, it's a 32-bit hexadecimal number. Because we have not specified the size, we are assuming that the simulator and the machine is using 32-bit as the default size. If so, this is a 32-bit hexadecimal number. We have specified the base format and the number. And in the second example, we have not specified the size, but the base format and the number we have specified. It's a 32-bit octal number. And the last example, there we don't specify either the size or the base format. So when you don't specify the base format, it is taken as a decimal number, and when you don't specify the size, it is set to be the default size used by the simulator and the machine. So this is a 32-bit decimal number. So that's about the number specification in Verilog. This part might be different from what you see in C. Something like this is not seen in C, since we are dealing with low level constructs like wires, registers, and electronic components that are used to implement digital circuits. You have to be specific about the number of bits and the base format and things like that. You have to be specific on them. So that is why we have syntax to specify a number precisely. And you can see X or Z values in Verilog. So this also is not something that you see in software programming languages like C. Here, when it comes to electrical signals, they can be sometimes unknown. If you consider about something like a flip-flop, at the beginning, like when you have not reset a flip-flop, the output of the flip-flop is not known. That you already know with the knowledge you already have gained in digital design course. So something like that is represented by X in Verilog. So an unknown value is denoted by an X. Also, there's a method to represent high impedance values in Verilog. That is, we use this Z. Verilog uses Z to represent the high impedance state. So high impedance state is actually the floating state. This occurs when you have not connected something to an input. So this, I think you have experienced in digital design labs as well. When you have not connected anything to the input is floating. We call it a floating state. So that floating state in Verilog is represented by or denoted by Z. If you are including X or Z inside a number specified in Verilog, if you are using an X or Z in a hexadecimal number, then X or Z represents 4 bits. So you are setting 4 bits to X or Z. and if it is placed inside a number represented in octal base, XOZ refers to 3 bits, and if you are including XOZ inside a binary number, then it sets 1 bit to XOZ. So this also will be more clear with the examples given in the slide. Now the first example, that is a 4-bit number. We are going to represent a 4-bit number in binary, and the number here is 100Z, and the last bit, so the last digit in the number is a Z. So you set the last bit or the least significant bit of the number to be in floating state, high impedance state, and only one bit is affected by the high impedance state. And the second example, it's a 12-bit number, and since you have apostrophe H, it's going to be represented in hexadecimal. There the real number is 13x. If you look at the last digit of the number, it's an X. So this X here represents 4 bits. So all 4 least significant bits are set to unknown. So that is what we discussed in third point about XOZ values. And then we can look at the underscore characters and the question marks. So you can place an underscore inside a number except the first character. So underscore characters would improve readability of numbers, and these underscore characters are ignored by Verilog. We use them to improve the readability of numbers. If the number is a large one which contains large number of digits, then we use this underscore sign to improve readability. And a question mark is the Verilog HDL alternative for Z. So instead of Z, we discussed a bit earlier, a little while ago, you can use this question mark as well. Now, two examples are given here related to this topic on this slide. If you look at the first example, it's a 12-bit number, and it's going to be represented in binary because we have this apostrophe B. And you can see inside the number two underscores. Two underscore characters are used inside the number. So this is used in fact to improve the readability. Because this is a 12-bit binary number, we have to use 12 digits, separate digits, 10 digits to represent this number. Since it's a large number or a lengthy number, we include underscore after every 4 digits to improve the readability. And then the question mark is equivalent to Z sign. So 4-bit binary number we are trying to represent, and 10 question mark. This one is equal to 4 apostrophe B 10ZZ. Okay, that was all about the number specification, and now we can look into strings in Verilog. As you all know, a string is a sequence of characters that are enclosed by double quotes. So strings are treated as a sequence of 1 byte ASCII values. So you know, one single character can be treated as 1 byte ASCII value. You have an example string here, hello Verilog world, which is enclosed by double quotes, and again there's another example about a valid string in Verilog. Now we'll look into identifiers and keywords in Verilog. First we can look into keywords. So keywords also you have seen in software programming languages like C. So the same principles apply here as well with keywords in Verilog. Keywords are special identifiers reserved to define the language construct, and all keywords in Verilog are in lowercase. So the examples for keywords are things like if, for, begin, end, and things like that. And we can now look into identifiers, how identifiers work in Verilog. Identifiers are names given to objects in Verilog so that they can be referenced in the design. So identifiers also you have seen in C. Identifiers are things like variable names. So identifiers are made up of alphanumeric characters, the underscore or the dollar sign. These are specific to Verilog. And identifiers are also case sensitive. And identifiers start with an alphabetic character or an underscore. So all identifiers have to be starting with an alphabetic character or an underscore. Here you can see two examples about identifiers and keywords. So the first one is reg value. First line of code is reg value. There the reg is a keyword. So this keyword you have not seen in C because these are specific to Verilog. So these keywords are specific to Verilog. And the second one is input CLK or input clock. So this input is again another keyword in Verilog. And value and CLK in these two examples are identifiers because they are names that we have given to these variables in fact. So you can think of them as variables for now. So the identifiers are the variable names basically. So that's about it regarding lexical conventions in Verilog. And now we can go to data types in Verilog. We can see what are the data types available in Verilog and how they work. First, we can look into the value set supported by Verilog. Verilog supports 4 values to model the functionality of real hardware. So with Verilog, what we are trying to do is modeling real hardware. And to model real hardware, we need a value set like this. Value levels can be 0, 1, X or Z. Now 0 is logic 0, that is false condition, and 1 is logic 1, true condition. So in digital electronics, all what you deal with is related to 0 and 1. And also in addition to 0 and 1, you need to have these other two values as well, X and Z. So X and Z, we have looked into them earlier as well. So X is there to represent unknown logic values and Z is there to represent high impedance of floating state values. So that's the value set available in Verilog. And then we can look into the first data type available in Verilog to represent nets. Nets represent connections between hardware elements. Now you all know that when you are going to design a circuit, a digital circuit, you need to connect modules together, modules or ICs or digital circuit components. You need to connect them together. So the component that we use in Verilog to connect two hardware elements together is called a wire or a net. And nets are declared with the keyword wire. So you need to use this keyword wire to declare a net. And nets get the output value of their drivers. If a net has no driver, it gets the value Z. So when we look at an example, you will understand this better. Now we have this AND gate. The inputs are B and C. The output of AND gate is A. Now we need to model this AND gate in Verilog. So you can model things like this in Verilog. In fact, not a single gate like this, but you will be modeling large circuits that contain thousands or millions of gates. So we'll see how we can define wires that helps us model this AND gate. There are three wires here, B, C and A. So to these B, C and A wires you will be connecting other components. So you need to define these wires using the keyword wire as given in the example. Wire A, you can say wire A to declare a wire called A, and the wire is the keyword and A is the identifier. Similarly, you can declare wires for or nets for B and C that you can do with wire B, comma C. So you have seen this syntax in C as well. When you want to declare multiple variables with the same data type, you can use the comma and then you can separate two variables with a comma. The same thing applies here as well. So wire BC will create or declare two wires called B and C. And now assume that you need to declare another net called D, another net or wire called D, and you need to assign 0 to that. Permanently you need to assign 0 to that. That is like you need to connect that wire to ground so that the logic value assigned to D will be always 0. So something like that you can do with the syntax given in the third example. Wire D is equal to 1 apostrophe B0. So 1 apostrophe B0, we already have looked into this syntax. This is how you specify a number in Verilog. This is a 1-bit number and we are going to assign 0. So at the declaration itself, you can assign a value to a wire. So this D is not something in the AND gate we have here, but it's there just to demonstrate how you can assign a logic value at the declaration itself. And the next data type we have in Verilog is registers. So registers represent data storage elements. So you have seen registers in real hardware, and there's a slight difference here. Actually, it's kind of like a big difference. So so that is also mentioned in the slide. This registers, you need to keep in mind that it's a data type that can store a value. So that's all what you need to keep in mind. Registers retain value until another value is placed onto them. Until you place something else, the value assigned to the register remains the same. So registers, in other words, you can say a register is a variable that can hold a value. This register data type is similar to usual variables that you see in C. So these register type variables can be declared by using the keyword reg, reg. So that is the keyword that you need to use to declare registers in Verilog. So couple of examples have been given here. In fact, it's like a example that tries to assign a value to a variable that has been declared as a register. So reg reset we have here, declare a variable reset that can hold its value, and then you assign 1 to this reset variable. So that to assign a value to a register, you need to have additional constructs such as the one given in the example, initial, begin, end. So those things are required, but this construct we'll discuss about it later. So for now, just ignore initial, begin and end keywords given here. If you look at the rest, then you can see reset is equal to 1 apostrophe B1. So that is 1 apostrophe B1 means a 1 bit number which is equal to logic 1, and you make reset equal to 1. So you can make a reg variable equal to a value by using a syntax like this. And after 100 time units, again there's something that you don't know yet, so that is hash 100. So this also we'll discuss later. Hash 100 basically means you need to wait for 100 time units before you do anything else. So hash 100 is there to represent that delay. Actually it's like a delay, it's a delay of 100 time units, and then after that we need to make reset equal to 0. So that you can do by having this syntax: reset is equal to 1 apostrophe b 0. What we are doing there is we are setting the reset. Now you need, as I told you at the beginning as well, you should not confuse the term registers in Verilog with hardware registers built from flip-flops, because there's a difference here. Because for these register data type variables, you don't have a clock or anything like that. For flip-flops, you all know that for flip-flops you need to have a clock, and at either the rising edge or the negative edge of the clock, what is there in the input is assigned to the output. So that is how a hardware register works. But this is not something like that. This is just a variable that can hold a value, so that you need to keep in mind. So you will understand how wires and registers work better when we go into real examples. And then vectors are there. So nets or register data types can be declared as vectors, multiple bits. So when you just declare a wire or a register with something like reg A, wire A, that is by default created as 1 bit wire or a 1 bit register. But if you need to define or declare a wire or a register that is multiple bits in width, you need to use this syntax: wire A. Now here wire A example, that is a scalar net variable, that is the size of this wire is 1 bit. And if you want to create a wire or set of wires, a set of wires is called a bus. So another name that is used to call a set of wires is a bus. And if you want to declare an 8-bit bus, the syntax you need to use is given in the second example: wire square bracket 7:0 closed square bracket bus. So this will create a set of wires that is like 8 wires. So this here we are declaring a bus. And if you want to declare 3 buses, each of which are 32 bits, then you can use the third example: wire 31 to 0, bus A, bus B, bus C. So with this you can create 3 buses, each of which are 32 bits in width. And then if you want to create a register variable that is 1 bit in size, or in other words you can say scalar register, that you can do with this syntax given in the fourth example: reg clock. So this will create 1 bit reg variable. And if you want to have multiple bits in the reg variable, then you have to use the syntax that we used for wires. That's how you can declare vectors, and then you have the ability to select a part of a vector. Now the first set of examples are the examples that we saw in previous slides regarding vectors. And if you want to select a particular bit in a bus, you can use the syntax given here in the second set of examples. Actually, the first example, bus A 7, this means you are selecting the 7th bit of the vector bus A. So, and if you want to select the 3 least significant bits of vector bus, you need to use this syntax in the second example, bus 2 to 0. So with this, what you will be doing is, from the bus we declared earlier, we are selecting the least significant 3 bits. So this syntax also will be useful when you are designing or modeling circuits with Verilog. You will understand how registers, wires, and vectors work properly or better when you when we go into implementing real circuits with Verilog. And there are other data types as well, which might be less common compared to the data types we discussed a bit earlier. So registers and wires are the most common type of data types that you will be using in Verilog, and you can use these data types as well: integer, real, and time. Uh, so integer, if you look at integer data type available in Verilog, the default for an integer is the host machine word size. This is like a 32-bit register. Uh, it's like it has to be at least 32 bits. So if the host machine word size is 32 bits, then it's going to be similar to a 32-bit reg variable. Integers can store signed values as well, while variables declared as reg could only store unsigned. So when you declare a variable as reg data type, then it can store only unsigned values. But if you assign a variable as integer, then you can store signed values as well. Integer counter, so there we are declaring an integer variable called counter, and we are assigning -1 to that counter next. So this initial keyword again appeared here, but since you don't know about that yet, you don't need to worry about it. And there's real data type available in Verilog. So this can be used to specify a number in decimal notation or in scientific notation. Some things like 3.14 and 3 into 10 to the power 6. So things like that you can use with real data type. So here we have defined a variable of real data type, real delta, and then we are assigning values to that delta variable. Delta is equal to 4 E10, that is 4 into 10 to the power 10, and then delta is equal to 2.13. There we are assigning 2.13 to the delta variable. And then we also have declared a variable of integer data type, and we are making integer I equal to delta at the end, so that so with this I will get the value 2, because a variable of type integer can hold only integers, so it will be rounded off to 2. 2.13 will be rounded off to 2. And then you have this time data type. Verilog simulation is done with respect to simulation time. So when you are doing simulations with Verilog, you will see that simulations are happening with respect to simulation time, and Time register data type can be used in Verilog to store the current simulation time. So if you get the need of saving the current simulation time, you can use a variable of type time. Simulation time is measured in terms of simulation seconds. Now there's an example given for this as well. Time save sim time. So save sim time is the identifier we are using, and then for save sim time we are assigning the current simulation time by using this syntax $time. So this $time is a special keyword that you can use in Verilog to get the current simulation time. So this also maybe we'll look at it later. So that's about time data type. And then you have strings, and you can use reg data type to store strings. You don't need a separate actually you don't have a separate data type to store strings in Verilog. You can use just reg data type to store strings as well. Uh, each character in the string takes up 8 bits, that is 1 byte, and if register width is greater than string size, bits to the left of the string is filled with zeros, and if register width is smaller than string size, leftmost bits in the string are truncated. And special characters such as new line character and tab character are allowed here in Verilog as well. Now there's an example given here about storing strings in Verilog. The example string we need to store is hello Verilog world, and if you count the number of characters in it, you can see that there are 19 characters in the string hello Verilog world. So to store this string, you need to declare a variable in register type, and this register has to be able to hold all these characters. That is, you need to use this syntax given in the first example, like given in the first line of this code, reg 18 to 18 to 1. We need this many number of bits, 18 to 18 number of bits to store this sentence. And the identifier we are using for this multiple bit register is string value, and then we are storing hello Verilog world by making string value equal to this particular string. So this is about strings in Verilog, and especially how you can store strings in Verilog. But you will see that things like strings, real, integer are not very commonly used constructs in Verilog, because we are dealing mostly with things that can be used to model real hardware. So most commonly we'll be using things like wires and reg variables in Verilog. So in fact in this course we'll most probably be using only wire and reg variable types, because those are the things that are that help us model real hardware circuits, because in hardware you are not going to store directly strings and things like that, but these things are there in Verilog to support other needs you might have. Things like when you want to print something out nicely, then you will need to uh, use strings. So there are the purposes, or there are the uses of strings. So most commonly we'll be using wires and registers. Now we are left with one topic, system tasks and compiler directives. So we can now look into what system tasks and compiler directives in Verilog are. So the system tasks are like special kind of commands that you can use in Verilog. So when we actually use these things, you will understand the functionality of these things better. So all system tasks appear in the form dollar and the keyword, and operations such as displaying on the screen, monitoring values of nets, stopping and finishing the simulation are done by system tasks. There are examples given here in the slides to system tasks available in Verilog. So bits to real, F display, F write, Inkscape, list, monitor, those things are system tasks available in Verilog. And most often we will use the system tasks display and monitor. In our labs we will use the system tasks display and monitor to display something or show an output to the user. And when you want to finish the simulation after certain time minutes, then you can use this $finish system task. So when we are actually using them, you will understand these things better. And the system task that you need to display some information to the user is $display. So think of a scenario like this. Now you have modeled the circuit in Verilog, and now you need to give certain inputs to the circuit, and you want to see whether the circuit is working properly. So how you can do this is by getting the output of the circuit displayed on monitor. So to do that, you can use this display system task. The format of display is very similar to printf in C. So you can actually send a formatting string to this display system task, and the way you uh, build that formatting string is very similar to what you do with printf in C. A display inserts a new line at the end of the string by default, and a display without any arguments produces a new line. So there's a usage example given here: $display p1, p2, p3, pn. Likewise, you can give what you need to print. And for display, there are format specifiers that you can use. So they are also very similar to, like some of them are similar to what you see in C, but there are additional formatting specifiers you can use with display command or display system task. You can use this %d to display a variable in decimal, and you can use %p to display a variable in binary, and you can refer to the rest of the table to get more information regarding formatting specifiers you can use with display command. And this is an example of how you can use display to print something to the user. You can use display hello Verilog world, this syntax, to display hello Verilog world out to the user. And display, if you want to display the current simulation time, you can use $display $time. So $time gives you the current simulation time. So we roughly looked at $time as well in one of the previous topics. So $time gives you the current simulation time, and if you want to display the current simulation time, then you can use this syntax. That is like combining two system tasks together. And there are a couple of more examples given here about what you can do with display. Here you are using here we are using formatting specifiers. At time %t, virtual address is %h. So now you need to provide the values that should be used to substitute %d and %h. For the first placeholder we are giving $time, and for the second placeholder we are giving virtual address. So this is very similar to what you do with printf in C. So there's another example, you can refer to that as well. And next we can look at compiler directives. in Verilog. So you have seen compile directives in C. Similarly, you have compiler directives in Verilog as well. All compiler directives are defined by using the apostrophe and then keyword construct. And here we'll focus only about two important directives, that is apostrophe define and apostrophe include. So you can use this apostrophe define to define a constant or something like that. Yeah, you have used this hash define construct in C. So here the same thing you can do with apostrophe define syntax. And if you want to define a constant named word size and assign value 32 to that, you can use the syntax given in the example, apostrophe define word size 32. And then the other compiler directive we are talking here is the include directive. This is also similar to the hash include construct you use in C. So if you want to include designs from other Verilog files, you can use the include compiler directive. And in the example, it has been given that you need to include the content in header Verilog file. Now we have not looked at real examples, so Verilog files are having the extension .v. So just like you have .c for C code, we have .v as the extension for Verilog files. So now we need to include header.v in our design. We can use this syntax. Now this is all about the basic concepts that I wanted to discuss, and maybe some of these concepts might be a bit confusing to you because this is like a whole new language that you are learning, and this is actually different to a typical software programming language. So you will understand these concepts better when we start doing something useful with Verilog. In coming parts, we will look into more details about what you can do with Verilog and how you can do them. Thank you.